Hello students, welcome to our physics class. So in the previous class we have studied about the meaning of cyclotron, principle of cyclotron, construction and working theory, merits and demerits of cyclotron, and a very important three-mark derivation, that is force acting on a current carrying conductor in the presence of magnetic field, that is F is equal to Bill sine theta. So this is moving charges and magnetism part 4. So in this class we are going to discuss about the next very important topic, that is Biot Savart law. Okay, well, let's start today's class. Biot Savart's law, that is also called the LAPLACE'S law. Actually, this law gives the magnitude of magnetic field around a current carrying conductor. So the magnitude of magnetic field around a current carrying conductor, so that can be determined by using this law. So Biot Savart's law, what is the significance of Biot Savart's law? Biot Savart's law gives the magnitude of magnetic field around a current carrying conductor. So first here let us consider a current carrying conductor XY as shown in the figure. So let us consider DL. First here let us consider DL. So DLB, a small portion of conductor. DLBA, small portion of conductor. Okay, so let us consider here, this is the midpoint of the conductor. So the direction of DL vector is tangent to the circular path. So here this is the direction of DL vector. So theta is the angle made by DL vector and DB vector. So this is the direction of magnetic field at point P. So P be the observation point near the current carrying wire. So the direction of magnetic field at point P, that can be determined by using right hand thumb rule. Actually here current flowing vertically upward direction. So the magnetic field lines around the current carrying wire. So that is like this. It is in anti-clockwise direction. So at this point, the direction of magnetic field is normally inverse. So DL vector and so R vector, this is the position vector. The R vector is the position vector of the observation point, or is the distance from the midpoint of the current element and the given point. So DL, let us consider this is a small element. DL be a small portion of the conductor. IDL is the current element. I into DL, this is called the current element. Current element. Okay, so R is the distance from the midpoint of the current element and the given point. So here what is the direction of magnetic field? That is normally inverse. Actually dB vector is perpendicular to plane containing two rotational vectors, that is DL vector and R vector. Suppose DL vector and R vector, that is in anti-clockwise direction, then the magnetic field is normally inwards. DL vector and OR vector rotated in clockwise, then the direction of magnetic field is normally outwards, right? That can be determined by using right hand thumb rule. The strike conductor that is held in the right hand thumb pointing in the direction of current, the fingers and circle which gives direction of the magnetic field. Okay, so according to Biot Savart's law, the magnitude of magnetic field dB vector at a point P, so near the current element. So according to the Biot Savart's law, according to Biot, according to Biot Savart's law, the magnitude of magnetic field, dB vector, the magnitude of magnetic field dB vector at a point P, magnitude of magnetic field dB vector at a point P near the current element is directly proportional to the strength of the current. The magnitude of magnetic field at point P near the current element is directly proportional to the strength of the current. Is it not? When the strength of the current flowing through the wire gradually increases, what happens? The magnetic field strength surrounding the wire also increases. If the strength of the current flowing through the wire gradually decreases, then the magnetic field strength surrounding the wire also gradually decreases. That means the magnetic field at a point P near the current element, ideal is the current element, so that is directly proportional to the strength of the current. And the second very important factor, that is directly proportional to the length of the current element. Suppose if the length of the current element increases, what happens? The magnetic field strength also increases. Length of the element decreases, the magnetic field strength decreases. That means the magnetic field near the current element is directly proportional to its length. And then the magnetic field, magnitude of magnetic field is directly proportional to sine of the angle between the current element, sine of the angle between, what is this? Current element and the line joining the midpoint of the current element and the given point. Okay, so the magnitude of magnetic field near the current element is directly proportional to sine of the angle between the current element and a line joining the midpoint of the current element and the given point. So, and finally, inversely proportional to square of the distance between the midpoint of the current element and the given point. Okay, so call this as equation number 1, call this as equation number 2, call this as equation number 3, and call this as equation number 4. Now combining all the 4 equations, so now combining equations 1, 2, 3 and 4, right? So then we get dB is proportional to IDL sine theta divided by or square. Okay, so remove the proportionality, we will get the proportionality constant. So dB is equal to K, K I D L sine theta divided by r square. So here K is called the proportionality constant. Actually, proportionality constant depends on the two very important factors. Number one, the medium existing between the point P and the midpoint of the current element, and also the system of units used. Number one, the medium between observation point and the midpoint of the current element. So, and the system of units used. So, the value of K is mu naught divided by 4 pi, and this value is 10 power minus 7, and this is very, very important. So, the unit of proportionality constant is Henry per meter or Tesla meter per ampere. Henry per meter or Tesla meter per ampere. Okay. So now the equation becomes dB. dB is equal to mu naught divided by mu naught is permeability of free space. So that determines the strength of magnetic field in free space. So dB is equal to mu naught divided by 4 pi IDL sine theta, ideal sine theta divided by r square. So this is the mathematical expression for magnitude of magnetic field around the current carrying wire, and this is a very, very important mathematical expression. dB is equal to mu naught divided by 4 pi, so IDL sine theta divided by r square. So in vector form, in vector form, in vector form, the Biot Savart's law, so that can be written in the form of dB vector is equal to mu naught divided by 4 pi I of dl vector cross or vector divided by or q, right? So apply the magnitude here. So the magnitude of cross product of two vectors, that is given by the product of magnitude of two vectors and the sign of the angle in between them. So after applying the magnitude, we will get RDL sine theta. So 1 get cancelled. So then we will get the same formula. That is dB is equal to mu naught divided by 4 pi ideal sine theta divided by r square. So this one having both magnitude and also the direction. So this is the magnitude of the magnetic field at a point near the current element. So this is the magnitude of magnetic field near the current element, that is in vector form, having both magnitude and also the direction. The direction of dB vector that can be determined by using right hand corkscrew rule or right hand thumb rule. Okay, actually here dB vector is this is the direction of dB vector. Cross mark indicates dB vector is normally inverse. So dB vector is perpendicular to this plane. Is it not? dB vector is normally inverse. dB vector is perpendicular to this plane, plane containing two rotational vectors, dl vector and r vector. Okay, so dl vector cross r vector means that is in clockwise. If it is in clockwise, what is the direction of magnetic field? So if it is in clockwise, then the direction of magnetic field is normally inwards. So if it is in anti-clockwise, the direction of magnetic field at this point is normally outwards. Okay. dl vector and r vector. So these are the rotational vectors. dl vector, r vector. Those are in anti-clockwise. Those are in clockwise. Then what is the direction of magnetic field? That is normally inwards. So suppose if dl vector or vector those are in anti-clockwise, then the direction of magnetic field is normally outwards. Okay, and this can also be written in the form of dB vector is equal to mu naught divided by 4 pi I of dl vector cross r cap divided by r square. So this is another form of Biot Savart's law in vector form. So again applied here the magnitude. So magnitude of dl vector cross r cap is magnitude of dl vector, magnitude of r cap sine theta. So magnitude of r cap is 1 because r cap is a unit vector, right? So this law gives the magnitude of magnetic field around the current carrying conductor, and this is very important. Okay, next let us discuss about the applications of Biot Savart's law. So the first application, that is derived expression for the magnetic induction at the center of a current carrying coil. So that can be determined by using Biot Savart's law. Okay. So first here, let us consider a current carrying loop. So here current flowing, that is in anti-clockwise direction. So what is the direction of magnetic field at the center? So that can be determined by using right hand thumb rule, right? So the fingers encircle which give the direction of current, and thumb pointing in the direction of the magnetic field. Fingers encircle which gives the direction of magnetic field, that is in anti-clockwise. The direction of magnetic field at this point at the center, that is normally outwards, right? Suppose the direction of current in the loop, that is clockwise, then the direction of magnetic field at the center, that is normally inwards. So here dot mark shows the direction of magnetic field is normally outwards. Okay, so let us consider a small current element here. This is small current element. So this is the observation point. Let us consider this point as P. Okay, this point as O. So again, ideal is the current element. So consider here a circular loop of radius, that is capital R. The magnetic field at the point P due to the current in this element. Okay, magnetic field at point P, that means at center, due to current in the small element dl. So that can be determined by using Biot Savart's law, right? So according to Biot Savart's law, magnetic field at P due to current in the element dl is given by dB. So this is the magnitude of magnetic field. dB is equal to mu naught divided by 4 pi I dl sine theta divided by r square. What is the meaning of r? R is the distance from the midpoint of the current element and the given point. So here that is capital R. So this is capital R square. What is the meaning of theta? Theta is the angle made by dl vector and r vector. Actually, dl vector is always tangential to the circular path. So what is the angle between dl vector? This is the radius vector. Angle between dl vector and r vector, that is exactly equal to 90 degrees. So actually the angle between dl vector and r vector at any point on the loop, that is same, that is 90 degrees. So now this expression becomes dB is equal to mu naught divided by 4 pi. So I dl sine 90 divided by r square. So dB is equal to mu naught divided by 4 pi I dl divided by r square. Sine 90 is 1. But we want the magnetic field at point P due to current in the entire loop. So what we have to do, just integrate this equation on both sides, right? So magnetic field at total magnetic field at P due to current in the loop. Total magnetic field at point P. This is magnetic field at point P due to current in the element dl. So total magnetic field at point P due to current in the entire loop is integration of dB is equal to integration of mu naught divided by 4 pi I dl divided by r square. So integration of dB is b. So here the constant terms take it as outside. Actually here mu naught divided by 4 pi I divided by even radius is also constant, right? So r square, that is taken as outside. Mu naught divided by 4 pi I divided by r square. Okay. Mu naught divided by 4 pi I divided by r square. This is constant. That is why take it as outside. Integration of dl. So b is equal to mu naught divided by 4 pi I divided by r square. Integration of dl is L. What is the meaning of L? L is the total length of this uh, circular current loop. So mu naught divided by 4 pi I divided by r square. So the length of the circular loop is 2 pi. What is the radius? R, right? This is the length of the loop, that is exactly equal to circumference. So R get cancels here, pi cancels, 2 ones are 2, 2s are. So finally we will get B is equal to mu naught I divided by 2R. Suppose if the coil has n number of turns. For one turn, so the magnetic field at the center is mu naught I divided by 2R. If the coil has n number of turns, then the magnetic field at the center is B is equal to mu naught Ni. B is equal to mu naught Ni divided by 2R. So this is magnetic field at the center of coil. So this is magnetic field at the center of the loop. Okay, so the next very important application, and this is very important for 5 mark. So derive the expression for magnetic field on the axis of a circular current loop. Derivation of magnetic field on axis of circular current loop. Okay. First here, let us consider a circular current loop. So here this thick line represents half of the turn is directed away from the plane of the screen, and remaining half turn is directed into the plane of the screen. Okay, actually the plane of the loop is perpendicular to this plane of the screen, right? So the plane of the loop, this point is very important. Actually this is three-dimensional diagram. Okay, so the plane of the loop, what is this loop? Plane of the loop that is perpendicular to the plane of this screen. Okay, actually off turn is directed away from the plane of the screen, and the remaining off turn is directed into the plane of the screen, and plane of the loop that is perpendicular to the plane of the screen. Okay, so after that let us consider two small circular elements, that is let us consider is AB and CD are two diametrically opposite current elements. So O is the center of the current loop. So actually here current flowing in anti-clockwise direction, and this is the axis of this current loop. What is this? Axis of the current loop. So O is the center of the current loop. So capital R, so this is a radius of the current loop. So P is the observation point. Actually at that point we have to calculate the magnetic field that is due to the current loop, circular current loop. So AB and CD are two diametrically opposite current elements. Each of length is dl. Okay. So let us consider here. This is the point E. E is the midpoint of current element AB, and F is the midpoint of the current element CD. E is the midpoint of the current element AB. F is the midpoint of the current element CD. Okay, so this is dl vector. So actually here dl vector is normally outwards. dl vector is normally outwards. So dl vector is always tangential to the circular path. So at point E, we have to draw a tangent. Actually, this is directed away from the plane of the screen. Okay. So in a similar way, direction of dl vector at point F is, that is normally inwards. So at point E, dl vector is normally outwards. At point F, dl vector is normally inwards. So R is the position vector of observation point. So R is the distance from the midpoint of the current element and the given point. Okay. So this is the position vector of the observation point. So what is the angle between DL vector and R vector? So actually DL vector is normally outwards. So DL vector or vector, so that is lies in a plane. So DB vector is perpendicular to the plane containing the two rotational vectors DL vector and R vector. So this point is also very important. The direction of magnetic field DB vector, that is perpendicular to a plane containing two rotational vectors. One is DL vector and another one is R vector. So what is the angle between DL vector and R vector? That is exactly equal to 90 degrees. Okay. So here DL vector is normally inwards. This is the direction of R vector. What is this? R vector. Position vector of the observation point. Distance from midpoint of the current element and the given point. So DL vector here normally inwards. So again the angle between DL vector and R vector is 90 degree. So and again DB vector, that is perpendicular to the plane containing two rotational vectors DL vector and R vector. Okay. So first here we have to calculate the value of small r by using Pythagoras theorem. So from figure, small r square is equal to capital R square plus x square. Is it not? Small r is equal to square root on both sides. So capital R square plus x square power 1 by 2. Power 1 by 2. Call this as equation number 1. So x is actually the distance from the center of the loop and the given point, observation point. So point under consideration. Actually at point P we have to calculate the magnetic field, that is due to circular current loop. So phi is the angle between R vector and x. Okay. So actually this is angle phi. What about this? This is 90 minus phi. So this angle is phi. DB vector is perpendicular to R vector. Perpendicular to the plane containing actually DL vector and R vector. The angle between R vector and DB vector is 90 degree. So this is 90 minus phi. So this angle should be equal to phi. Right? So DB vector does not lie along x and y axis. So that is why DB vector that should be split into two rectangular components. This is x axis. This is y. This one is y dash. Okay. So this is angle phi. What is this? Perpendicular. Let us consider your imaginary rectangle. So this is perpendicular, hypotenuse. This one is base. Base component is dB cos phi, right? And again, this angle is phi. This is perpendicular. Perpendicular component is dB sin phi. So dB vector along PM, that is actually splits into two rectangular components. dB cos phi along PY and dB sin phi along PX direction. So in a similar way, dB vector along Pn, let us consider this is n. Okay. So dB vector along Pn, that is also splits into two rectangular components, dB cos phi along Py dash and dB sin phi along Px. Okay. So here is also we have to choose an imaginary rectangle. So this is perpendicular, this one is hypotenuse, this one is base. Base component is dB cos phi. So perpendicular component is dB sin phi. So dB vector along PM, that is splits into two rectangular components, dB cos phi and dB sin phi, and dB vector along PM is also splits into two rectangular components, dB cos phi and dB sin phi. So from this figure, what is the value of sin phi? Sin phi is equal to sin phi in the right angle triangle OEP. So in the triangle OEP, sin phi is capital R perpendicular divided by hypotenuse. Capital R divided by small r. So call this as equation number 2. Okay. So according to Biot Savart's law, according to Biot Savart's law, magnetic field at point P due to current in the element AB. Magnetic field at point P due to current in element AB is dB is equal to mu naught divided by 4 pi IDL sine theta. Theta is the angle between DL vector and R vector, that is 90, sine 90 divided by square of the distance between midpoint of the current element and the given point, that is small r. So ideal sine 90 divided by R square. So dB is equal to mu naught divided by 4 pi IDL divided by R square. Call this as equation number 1. Okay. So similarly, the magnetic field at the point P due to the current in the element CD is also same, that is dB is equal to mu naught divided by 4 pi IDL divided by R square. Ideal sine 90, sine 90 is 1. Ideal divided by R square. So call this as equation number 2. Okay. Now dB vector along PM. dB vector that is along dB vector along PM. This is splits into two rectangular components. One is dB cos phi, and this is along which direction? dB cos phi, that is along py direction, and another one is dB sin phi. So dB sin phi, so that is along px direction, and dB vector along P Pn, dB vector along Pn. So this is also splits into the two rectangular components. One is dB cos phi, dB cos phi, and this is along dB cos phi along Py dash. Another one is dB sin phi, dB sin phi along Px direction. Okay, so the magnetic field along Py and Py dash both are equal and quite opposite, right? So actually here the components dB cos phi along Py and Py dash get cancelled with each other. each other. Why? Because both are equal and quite opposite. So dB cos phi along Py and dB cos phi along Py dash both are equal and quite opposite. So that is why the components are get cancelled with each other. But dB sin phi along Px or dB sin phi along Px both are moving in the same direction. So what is the resultant magnetic field? So the resultant magnetic field at P due to the current in the elements, current in both the AB and CD is dB sin phi plus dB sin phi, right? Because both are moving in the same direction. But actually, we want the resultant magnetic field at point P due to the current in the entire loop. So the resultant magnetic field at P due to the current in the loop is, so what we have to do, just integrate. So B is equal to integration of dB sin phi. Okay, just for one pair of opposite corners. So the resultant magnetic field is dB sin phi plus dB sin phi. Actually, a circular loop having so many diametrically opposite current elements. For each pair, we will get dB sin phi plus dB sin phi. For the entire loop, that is just integration of dB sin phi. B is the resultant magnetic field at point P due to current in the entire loop. Okay, so B is equal to integration of dB is mu naught divided by 4 pi I dl divided by r square. What is the value of sin phi? Sin phi is capital R divided by small r. So B is equal to the constant terms, take it as outside. So mu naught divided by 4 pi I dl divided by, actually dl is not constant, dl is variable. So capital R is constant, take it as outside. R square into R, that is R cube, integration of dl. Okay, integration of dl is L. The next step, B is equal to mu naught divided by 4 pi I capital R divided by, actually small r value is r square plus x square power 1 by 2 whole power 3 into integration of dl is L. So B is equal to mu naught divided by 4 pi I r. So L is the length of the loop, that is 2 pi r divided by r square plus x square whole power 3 by 2. So finally, we will get expression, that is B is equal to mu naught divided by 4 pi 2 pi I r square divided by r square plus x square whole power 3 by 2. Okay, so this is Mathematical expression for magnetic field at a point due to the current and the loop. So this is the magnitude of magnetic field at point P due to the current in the loop. So what is the direction of magnetic field at point P? That is directed from left to right. So actually the direction can be determined by using uh, right hand thumb rule. Actually here the fingers and circle which gives the direction of current, that is in anti-clockwise, thumb, extended thumb pointing in the direction of the magnetic field, that is from left to right. Suppose the current flowing in the loop, that is in clockwise direction of magnetic field, that is the reverse, that is from right to left. Okay, so in vector form, in vector form, the direction of magnetic field is, that is from left to right. So in vector form, the expression for magnetic field at point P is B vector is equal to mu naught divided by 4 pi 2 pi I r square divided by r square plus x square whole power 3 by 2 into r cap. So r cap is a unit vector. Okay, indicates direction of the resultant magnetic field at point P due to the current in the loop. R cap is unit vector directed directed along directed along Px. Suppose if the coil has n number of turns. Suppose if the coil has n number of turns, then what is the magnetic field at point P? That is B is equal to mu naught divided by 4 pi 2 pi n I r square 2 pi n I r square all divided by r square plus x square power 3 by 2. So this is magnetic field at point P on the axis of current loop. This is magnetic field at point P due to the current in the coil. Okay, so this is the mathematical expression for magnetic field at a point P on the axis of current loop. So this is a mathematical expression for magnetic field at a point P on the axis of a current carrying coil. Okay, so in vector form again, B vector is equal to mu naught divided by 4 pi 2 pi ni r square divided by r square plus x square power 3 by 2 into r cap. R cap is a unit vector, so indicates direction of magnetic field at a point P on the axis of current coil, that is along Px direction. And this derivation is very important for 5 mark. Okay, thank you.